Hey everyone, it's Justin again. In the last video, you learned how to evaluate step functions, which are a type of piecewise function. In this video, we're going to be extending that knowledge to more complicated piecewise functions. Previously, you saw step functions, which look something like this. Most piecewise functions, however, are more like this. You've got domain intervals on one side, and an expression that can be used to find the outputs on each interval. Evaluating at specific inputs is just like evaluating other functions, with an additional piece, figuring out which expression to use. For this piecewise function, what's the output if the input is 3? First, we need to find which interval 3 falls into. That should be pretty obvious. 3 is greater than 1. So since our input falls into that interval, the output will be based on its related expression, 2x minus 2. From here, we simply plug in 3 and solve, and we get 4. So when the input is 3, the output is 4. What if we want where the input is negative 8? Well, negative 8 falls into that first interval, where x is less than or equal to 1. So we'll be using that expression, negative 2x plus 2. We plug in negative 8, and we get an output of 18. What if the input is 1? Which interval would we use then? The one where x can be equal to 1, of course. And we input 1 into that first equation, and we get an output of 0. Some piecewise functions have more pieces, but the process still works the same. So what's the output here for an input of negative 4? Negative 4 falls into the interval x is less than negative 1, so we'll be using this first expression. When we use negative 4 for x, we get an output of negative 3. Let's take it up a notch now. What is the output for an input of 2.718? What's that? It's too many decimals? I don't know about that. After all, that would be in the interval from negative 1 to 3. And on that interval, the output is automatically 2, just like a step function. Okay, yeah, so that was a little too easy. How about an input of 7.4? First, we find the interval that includes it, and then plug it into the appropriate expression. Negative 7.4 plus 2 is negative 5.4. Like I said before, it's just like evaluating other functions. You just have to decide which expression to use first. So we've learned before that there are multiple ways to describe an interval, and that applies to piecewise intervals too. Typically, you'll see intervals in inequality form, just like we've been using, but sometimes you'll see interval notation instead. Aside from this new symbol here, this is the same interval notation that you already know. This symbol just means is an element of, or even more simply, is in. So this first domain interval just reads if x is in the interval between negative infinity and negative 1. It means the same thing as x is less than negative 1. It's just a different way of writing it. The other two read if x is in the interval from negative 1 to 3, and if x is in the interval between 3 and infinity. So let's try an example with interval notation. Pause the video now and see if you can evaluate the piecewise function at these 3 inputs. Were you able to figure out the right intervals to use? 0 falls between negative infinity and 1. So we plug it into the function, and 0 plus 3 is 3. The input 1 could fall under either the first or second interval, but the first interval has a bracket on the 1, which means that it belongs there, not in the interval where it has a parenthesis. So we substitute 1 for x, and 1 plus 3 gives us 4. Finally, 5 fits into that last interval between 4 and infinity, so we use 5 for x, and we get that negative 15 plus 15 is 0. Evaluating piecewise functions is super easy. You just find the right interval, and then use the expression that goes with it. try writing your own piecewise function and evaluate different inputs with that. Evaluating piecewise functions gets even easier when you graph the piecewise functions. So the next video is going to focus on that. See you then.